Okay, let's start talking about exponential functions. The first thing I want to do is just have you recall some properties that exponentials have here. Remember that the number on the bottom here is with the regular script will be what? Will be called the base, and the superscript number is called the exponent, right? So the base and the exponent, or power as some people call it. The first property, just as a review here, this is stuff you should know already, but let's review it. The product rule: if I multiply two exponentials with a common base, what do? You add the exponents. I will be putting this online for your review, by the way. This, in fact, I'll do this entire PowerPoint here. Okay, if I have two exponentials with a common base and I want to take their quotient, then what I'm going to do is take that base and raise it to the power, which is the difference of the two powers here. The power of the numerator minus the power of the denominator. I should throw in right now what I'm going to be doing here throughout our discussion of exponential functions. The base is always going to be a positive number which is not equal to 1. A positive number which is not equal to 1. Okay? So this would preclude dividing by 0 or anything like that in the quotient rule. Okay? How about a power rule for products? If I have two bases, a, b, being raised to the m power here, or a base that is a product here, I could actually do what? I could break it into the product of the first base to the m power times the second base to the m power. Here, if I've got a quotient, a over b, and I'm raising that to the m power, then I do what? I can take the quotient of the exponentials, a to the m divided by b to the m. Okay? Power rule for exponential forms. This is a base to a power to a power. If I've got a base to a power and I take that result and raise that to a power, what I can do is preserve the original base a and raise it to which power? The product of the two powers here, the product of the two exponents. So a to the m to the n is a to the mn. Okay? I give concrete applications of all these down the second or the last column here. How about a to the 0 power? You remember that was going to be what? 1. Okay. A to the minus m, 1 over x to the m. So if you've got negative exponents, you think of those as reciprocals here. I just noticed a typo. This should be x to the minus third is 1 over x cubed. Oh well. Rational exponents, a to the n over m. That's the mth root, right, of a to the n, or the mth root of a raised to the n power. Okay, so all this stuff should be review for you. Let's go on and discuss my definition here of exponential functions. Okay, all right, let's try it here. What's an exponential function? Okay, definitions differ slightly from author to author. This is the way we're going to do it. Y equals f of x is a times b to the cx power here. Notice in this discussion here, b is my base, so think of b for base, okay? A is just a constant multiplier out front, and the exponent is going to be c times x, okay? You could actually rewrite this and go b to the c power raised to the x power, base to a power to a power. But many problems naturally occur in this form, so I'm going to go ahead and write my exponential functions this way. Okay, so we'll see examples here why this form naturally occurs here, even though technically this could be simplified. Here a, b, and c are constants. A is going to be greater than 0 in our definitions. In theory, a could be a negative number, but none of our problems are going to involve that. Okay. I mentioned this already, that my bases are going to be greater than 0 and not equal to 1. I'll explain why you need the base to be greater than 0. That's to make sure this doesn't become complex valued, okay? For example, if that was negative 1 to the half power, that would be the square root of negative 1, which is I, okay? We don't want that kind of stuff happening here. In higher mathematics, you can do that, but this is not that situation we're dealing with. The reason why we want b to be other than 1 to any power is still 1, and this would be completely trivial, and we shall see later that exponential functions are always 1 to 1 under these conditions. But if you had b equal to 1, you would just basically get a flat line. Okay? We'll see more on that here. I want to throw in another quick comment here. The independent variable I'm writing here as x currently. Later on, we will often have t as the independent variable, t representing time quite often. Okay? All right, so anyways, that's what they look like. Okay? Here's some properties of exponential functions that we will see throughout. Exponential functions are always continuous. So that means you could draw the graph of y equals f of x that I had before without lifting your pen from the paper, right? So there's no jumps and no holes in the graph, okay? Exponential functions are also smooth. This means in addition to being continuous, no jumps or holes, it also has no corners or anything like that. Technically, we would say in calculus it is differentiable, meaning there's a well-defined tangent line to each point. But just think of it as smooth, no corners, okay? So it's not jagged or anything like that. Exponential functions always have a domain, which is all real numbers. There I've used our interval notation. Exponential functions, okay, according to my definition up there, always have a range being all positive real numbers, greater than or equal, not greater than or equal to 0, but strictly greater than 0. Notice in this, I'm using interval notation again. I'm using parentheses here, right? So you can't actually get 0 out of this thing under at least these conditions here. A is greater than 0 and b of the appropriate type here. Okay, exponential functions always have a horizontal asymptote, which is the x-axis, so the line y equals 0. Okay, they always have a horizontal asymptote. Okay, exponential functions are increasing if the base is greater than 1 and decreasing if the base is between 0 and 1. Okay, we will see some graphs of that and what's going on there in just a little bit. Okay, another thing, exponential functions are always 1-to-1. What does that mean? Remember, 1-to-1 functions corresponding to every x value, there's one y and vice versa. Graphically, you can think of this would satisfy both the vertical and horizontal line tests. Okay, so every vertical line will intersect the graph at most one point, and in fact exactly one point because the domain is all real numbers. But every horizontal line will intersect the graph at most 1 point. Okay? All right, so exponential functions are always 1-to-1. Do you remember 1-to-1 functions always have what? Inverse functions. Yes, inverse functions. We're going to see that the inverse of a power function, which is a particular type of exponential function, is going to be what we call a logarithmic function. It's not going to be hard at all. Okay? Let's go ahead. Here's power functions, as a matter of fact. These are simplified exponential functions where I've just got y equals f of x is some base to the power. Okay? These functions are just particular functions, types of exponential functions, so it's going to have all these same properties. Okay? Alrighty? So y equals b to the x, a little bit simpler form here. Okay? What would the a be? The a would be 1, right? The b would be, b, and the c would be 1. Okay? By the way, I should have maybe mentioned this originally. There's no restrictions on c here. There's no restrictions on the c, other than, being a real number. Okay? Anyways, back to power functions. Y equals b to the x. These will be the first ones we consider the graphs of. Let me throw this in here. Do you remember how to get the y-axis reflection of a function? You replace x by what? Minus x, right? So if I have y equals f of x defined as above, y equals negative x would be, y equals f of negative x would be what? The y-axis reflection. So I replace x by minus x here, and I would get b to the minus x power. Now, let me have you recall that b to the minus 1 power raised to the x power would be what? Well, we would take the product of the two, right? Negative 1 times x is negative x. So right here, this is a valid equal sign. What's b to the minus 1 power, though? Remember, it's the reciprocal, right? So this actually becomes y equals the reciprocal base to the x power, okay? So the y-axis reflection is actually what? an exponential, or in this case, a power function where what? The base has been replaced by its reciprocal. Okay? Alrighty. Here, I'm going to go ahead and give you a graph of y equals 2 to the x here. Okay? So this is the idea, y equals 2 to the x. And here I've actually have a table off of Desmos of function values. So here I start at -3. 2 to the -3 would be 1 over 2 cubed. That'd be 1/8. In decimals, that's 0.125. And you see that point has been graphed here. X is -2. That would be what? 1 over 2 squared. That's 1/4, 0.25, and so forth on down. Okay? Till what? I've got this last point here graphed. 2 to the 3rd power is 8. And you see here that this is what? What's our base in this particular power function? Our base is 2. 2 is greater than 1, and notice that this is in fact what? An increasing function. Yes, the y values get larger as we move from left to right, all right? Correct? Okay, do you also see here, now you can graph this on Desmos yourself here, every time I move 1 unit to the left here, I'm actually cutting the y value in half. What I'm going to end up with is what I stated before, right? I said every exponential function is going to have what? A horizontal asymptote being the x-axis, and you can see that right here. This is asymptotic too. There's always a little gap between the x-axis and the actual function though, right? Okay, now if I was to project this thing onto the y-axis, see what I would get? Everything from 0 to infinity, not including 0. That means, once again, you can see that the range is from 0 to infinity, not including 0. So all positive real numbers. Okay? The domain, project this onto the x-axis, you get all real numbers. Now let's look at another graph here. I wanted to talk about this. Remember, I said if I replace x by -x, I get the y-axis reflection. And look at these two graphs together. Y equals 2 to the x and y equals 2 to the -x. They're indeed what? Y-axis reflections of each other. Notice here, the value of the function at 3 is 8, but the value of the function here at -3 is 8. Okay, and so forth. So compare these two tables. Okay? Alrighty? Very clear here, hopefully. Now, you should graph these on your own. That's a good thing to do. Here, I wanted to throw this in also. Remember how I said what? 2 to the -x power ought to be the same as y equals the reciprocal base to the x power. This is 1/2 to the x power. Well, first I graphed y equals 2 to the -x, and then over here, I haven't actually graphed that yet, but we'll see when I graph that one. Oops, it's exactly the same. Y equals 1/2 to the x power. See the two? They're exactly the same. Actually, my graph is stretched out when I put it on this PowerPoint. But other than that, you see that it's the same. Okay? All right. Let's talk about, this may seem strange, I'm going to talk about linear functions here for a second. The hallmark feature of linear functions, if y equals f of x is a linear function, then a fixed change, delta x, remember delta stands for change in x? Okay, delta x is in the independent variable, always leads to the same difference, delta y, in the values of the dependent variable, the y values, regardless of the original value of the independent variable. So delta y is f at x naught plus delta x minus f at x naught. It's always the same delta y regardless of what x naught is. In fact, I want you guys to try to prove this if you can. What does a linear function look like? Mx plus b, right? Mx plus b. In fact, it's not hard to show that the change in y is m times whatever the change in x was. Okay, delta y equals m times delta x. Why do I mention this? Why am I talking about linear functions? Well, I'm going to show you the hallmark feature of exponential functions. If y equals f of x is an exponential function, right, like I defined originally up there, then a fixed change, delta x, in the independent variable always leads to the same ratio in the values of the dependent variable, regardless of the original value of the independent variable. In other words, I'm not taking differences here, I'm taking ratios. F of x naught plus delta x divided by f of x naught is always some factor k. K is going to be greater than 0 is constant for all the real x naught, okay? Or equivalently, I wrote it this way. The function evaluated at x naught plus delta x is k times the function at the original value x naught. And again, this holds for all real x naught. Okay? So you see how these are kind of similar in that sense, right? Okay? In their hallmark features, only one, you're talking about what? Differences in the function. And the other one that's always fixed. See, I could have called this, it wouldn't have been as suggested, but I could have called that k. Okay? That wouldn't have been very logical here. Maybe I should have called this q or something for quotient. I don't know. But this is a ratio of y values. Okay? Maybe I should have called it something like an m, but that would suggest too much, maybe. Okay? But anyways, you can see how they're similar in that sense. Only here, you're dealing with a ratio of function values. Okay? Examples of exponential growth we'll be looking at. Exponential growth, we're going to have where the base is greater than 1. That's where the function is increasing. We'll have some population problems and some compound interest problems. Okay, and then some just abstract problems that I didn't mention. And exponential decay, this is where the base is between 0 and 1. This will be in radioactive decay and heat change over time. There'll be some examples. Alrighty? Okay, that should be good for starters.